Welcome to The Debate. Our discussion today centers on the huge implications of this recent paper, Video Models Are Zero-Shot Learners and Reasoners. We're focusing particularly on the emergent capabilities shown by the generative video model VO3. And the core claim here really is that these video models are basically following the same developmental path as large language models scaling up, to become these unified generalist foundation models specifically for vision.
So the central question, I think, especially for the AI research community, is whether the progress we're seeing in VO3, the qualitative results look impressive, right? But is it a definitive technical leap towards replacing specialized vision models? Or do the quantitative performance lags and some of the specific architectural issues mean that this GPT-3 moment for vision is still, premature?
I'm going to argue that the sheer breadth and the scaling of capabilities that VO3 demonstrates across perception, modeling, manipulation, and reasoning pretty much confirms this paradigm shift is coming, maybe sooner than we think. The technical approach, training these massive generative models on web-scale spatiotemporal data, seems fundamentally sound. Okay, I absolutely agree that the pace of progress from VO2 to VO3 is, massive. That's undeniable. But my position is slightly different. While the capabilities are broad, sure, the performance ceiling, when you really look at the numbers, is still significantly below specialized state-of-the-art models. And when we really drill down into the low-level details, things like the need for very specific, brittle prompt engineering, and these systematic biases we see in tasks needing precision, like abstract geometry, it suggests that these video models aren't quite the robust, generalist replacements we might hope for, or at least not yet. We really need to scrutinize the quantitative side and the architectural constraints before, declaring victory.
I see why you'd emphasize those constraints, but let's try and ground this in the technical reality of the scaling itself. The data, it confirms a consistent and frankly rapid performance lift just by moving from VO2 to VO3. And this, for me, really validates the core idea that the LLM primitive, this concept of large generative training on vast unstructured data, actually works pretty successfully in the vision domain because its architecture fundamentally can process both spatial and temporal information at the same time.
Right.
VO3 handles this whole spectrum of tasks, 62 qualitative and 7 quantitative that it was. And this is key, neither trained nor adapted for. So we're observing these complex emergent abilities that seem to span the entire vision stack. Things like interpreting ambiguous images, the Dalmatian illusion example, modeling quite sophisticated intuitive physics like buoyancy or air resistance, and even complex manipulation tasks like zero-shot in-painting or style transfer. The technical takeaway for me is that this kind of video architecture provides a richer, a more general foundation than static image models ever could, unlocking these emergent skills that just go beyond specific task-driven training.
Okay, that's a powerful overview of the breadth, I grant you that. But let's talk reliability. The term unified foundation model implies a certain robustness, a consistency, that I'm not sure the current metrics fully support. Let's take performance on core vision tasks. Edge detection, for example. VO3 achieved an OIS at 10 of 0.77. Now, OIS at 10, just for listeners, that's object instance segmentation accuracy measured across 10 output frames, basically how well it finds object boundaries over time. Now, 0.77 is, remarkable for a zero-shot generalized model. I'll give you that. But task-specific state-of-the-art models, they're hitting around 0.90. That performance lag isn't trivial, it's substantial. And maybe even more critically, the way they evaluate it masks some significant limitations for practical use. The benchmark relies really heavily on this best frame metric to showcase the model's competence ceiling, but, as the paper itself acknowledges, a user in the real world, they don't know which frame is the best frame. You can't pick it out beforehand. So if we shift to the metric that's actually usable in practice, the last frame metric, the final output a user actually gets, the performance drops a lot. For class-agnostic segmentation on the LVIS subset, which is a common benchmark, the MIOU, that's mean intersection over union, it plummets from 0.74 using the best frame way down to 0.56 using the last frame. That's an 18-point drop. It's a pretty severe indicator that the model lacks consistent control over its output across time, making it unreliable as a foundational replacement right now.
Okay, I see that point about the best frame versus last frame delta, but I tend to view that more as a challenge of temporal control and optimization, something we can likely improve rather than a fundamental structural ceiling on its competence. I think we also need to look at the architectural advantages, where frankly, specialized models just fundamentally fail to compete. The key technical innovation here, I think, is VO3's ability to tackle sequence reasoning. Let's look at the maze-solving task in Figure 7. VO3's success rate on standard 5x5 mazes is 78% pass at 10. That drastically surpasses VO2, which was only at 14%. Okay, fine, internal comparison. But more relevantly, VO3 solves irregular mazes, 75% pass at 10, where an image editing model like Nano Banana just fails completely. It can't do it. This success in graph traversal, I think, proves that the temporal mechanism, this frame-by-frame generation, is doing something fundamentally new. And what's more, VO3 seems to struggle less than even powerful LLMs like Gemini 2.5 Pro when the maze is presented visually, image to text, or I to T. That highlights a definitive advantage of solving a sequential visual problem step by step in its native visual medium.
That's a compelling specific example with the mazes, but I'm not fully convinced by that line of reasoning because it seems to focus on a narrow success case while maybe ignoring the extreme fragility revealed elsewhere, particularly in the prompt sensitivity analysis. Yes, it solves mazes sometimes, but look at the variance they documented. On the visual symmetry task, just changing the prompt phrasing led to performance swings of 40 to 64 percentage points across different test splits. That's huge.
This kind of variance shows that the capability being observed isn't necessarily robustly internalized. It seems heavily dependent on brittle external prompt engineering. Researchers are having to use really complex control instructions like asking for a motion outlet just to manage the model's built-in bias towards animation, or specifying incredibly detailed camera controls like static camera, no zoom, no pan, no dolly. A truly robust generalist foundation model, you'd think, should have internalized these kinds of structural controls. Instead, we're basically forced to provide these meta-instructions that drastically affect its ability to complete a core geometric task. That doesn't scream robustness to me.
Well, I think we actually agree that the sequence of generation is the crucial technical differentiator here. This frame-by-frame process, what they're calling chain of frames, or COF, is effectively the computational analog to chain of thought, COT, reasoning that we see in LLMs. The generative objective itself, predicting the next plausible frame in space and time, inherently encourages this kind of sequential problem solving. And this mechanism, derived directly from the architecture and the training objective, is what allows it to approach problems like sequencing and visual graph traversal in the first place.
The model's internal world model? While COF might be the framework, the generated output often violates pretty fundamental mathematical and physical laws, and that suggests the underlying world model, the modeling capability they talk about, is still fundamentally flawed, or at least imprecise. We see these systematic failures in core geometric and physical modeling that are frankly concerning for a model aiming for generalization. Take rigid body physics. The classic piano movers problem failure they show, it involves the couch literally violating rigid body integrity. It sort of deforms and squeezes through the doorway rather than correctly executing the necessary rotation and translation.
This really suggests the model prioritizes generating a plausible, smooth video continuation, which is a feature of its generative training, over preserving fixed geometric constraints. And when we move to abstract geometry, the failure seems even more pronounced. For visual analogy solving, Figure 9 VO3 performs below chance. The baseline is 0.33 on reflect and rotate analogies. Wait, hold on. Performing below chance, that doesn't just mean it's guessing randomly.
It points towards an actively erroneous systematic bias in how it tries to apply abstract geometric transformations, seemingly along the wrong axes. This doesn't feel like a minor data bug. To me, that looks more like a core architectural flaw in abstraction and modeling, possibly stemming directly from its training objective.
I absolutely acknowledge that the model currently struggles, sometimes significantly, with mathematically precise abstract reasoning. And yes, it sometimes favors generative plausibility over strict adherence to rigid physics. I see that. However, I think we have to view these shortcomings through the lens of future optimization potential. The scaling results presented are actually deeply encouraging. We see that pass at 10 is consistently higher than pass at 1 across tasks. And importantly, the scaling curves show no signs of a plateau. This strongly suggests the current performance ceiling is likely transient. The underlying competence, the zero-shot capacity to even attempt these complex tasks across the board, that's the hard-won foundation.
And the performance itself can likely be significantly boosted by adopting standard optimization methods we've already seen work well in LLMs, things like inference time scaling, maybe self-refinement loops, or post-training with automatic verifiers. The architecture, I believe, has proven its generalized knowledge capacity, even if the model right now is expensive and maybe a bit of a jack-of-many-trades, master of few.
That optimization trajectory is plausible, yes, but my worry is that focusing too much on the scaling curve potentially overlooks a critical architectural reality here, the inherent conflict between its generative mechanism and the requirements of static vision tasks. VO seems to have this pervasive, strong prior to keep things moving. It wants to animate. This animation bias, which seems inherent to its cohave generative objective, it's always trying to predict the next frame, is actually detrimental to image-to-image tasks like edge detection or segmentation, where the desired output must be perfectly static and stable.
Right.
This architectural bias has to be actively fought against, using complex prompting techniques that motion outlet trick again if you want the model to perform static vision tasks well. Now, if the model's fundamental nature has to be mitigated so heavily just to perform tasks that specialized models like SMV2 handle reliably and naturally, it fundamentally hinders its ability to truly replace them in practice. That bias itself, I think, proves that generalization in this specific architecture is currently unreliable for foundational vision tasks that require absolute precision and stability.
Look, I maintain that VO3 represents a clear inflection point, despite the existing biases and challenges. The rapid performance increase from VO2 to VO3, combined with the sheer consistency of zero-shot success across that full stack perception, modeling, manipulation, and reasoning, demonstrates pretty clearly that these video models are acquiring the comprehensive world knowledge needed for general vision. The existing issues like prompt sensitivity and these architectural biases, I see them as engineering challenges that will likely diminish as scale increases and as we develop better control mechanisms, ultimately leading us toward that generalist foundation model for vision.
And I maintain that the data confirms extraordinary progress, absolutely. But it also clearly highlights that generalization in these deep generative models is at present unreliable, particularly for abstract reasoning and tasks demanding mathematically precise physical modeling. Until these underlying architectural biases like that animation prior and the really significant gap between the unreliable best frame ceiling and the practical last frame performance are resolved, specialized models simply remain the practical necessity for many real-world applications. Understanding these nuanced limitations, I think, is absolutely crucial for directing future research investment wisely in vision architectures.